Okay, so in this video, we're going to talk about another simple machine, and this time that simple machine is gears. So a gear is again, type of simple machine that's used to manipulate the magnitude, or the size, or the direction of a force. And gears are used in combination, so you'll never find a gear in isolation working by itself. They're used together, and they're linked together by their teeth. And when we have a system of linked gears, we call this a gear train. So referring to our illustration, here we can see a single gear, and then we can see the teeth that comprise this gear. Then if we see the interface, or the place where one gear meets another, we can see how these teeth work to mesh together. Now, when we have this system, these multiple gears that are linked together, this is again called a gear train. So by using interlocking teeth that mesh with another gear, rotational force can be transmitted between gears. So for example, if we have this gear rotating, the gear on the far left, that means rotational force will see that the adjacent gear rotates, and so will all other gears that are meshed in this system. So before we continue our discussion and talk about gear ratios, I want to talk about 3 important things you should know, understand, and remember about meshed gears, whether it be 2 meshed gears or a system of meshed gears. So the first important thing to know is that for any 2 meshed gears, they will rotate in opposite directions. So for example, if we refer to our illustration, we can look at the meshing of gear A and gear G. So therefore, we know these 2 gears must be rotating in opposite directions. So for example, if gear G is rotating clockwise, then we know that gear A must be rotating counterclockwise. The second important thing to know is that when 2 gears are directly linked, their tangential velocities are always the same. So first of all, what do we mean by tangential velocity? Well, we're talking about the velocity that is tangent to 2 meshed gears. So this velocity will be the same for each gear. So again, for example, looking at the meshing of gear A and gear G, these will both have the tangential velocity VA. Now, we can also consider that gear G is also meshed with gear B. So these 2 will have the same tangential velocity, which is VB. But because this is a system of meshed gears, this also means that VA is equal to VB. So these are all the same tangential velocity. Then lastly, the third important thing to know is that larger gears rotate more slowly than smaller gears if they have the same tangential velocity. So for example, again, we can, for a final time, look at gear A and gear G, and we can see that gear A is much smaller than gear G, and they have the same tangential velocity, which means the rotational speed of gear A will be greater than that of gear G. Okay, now we can move on to talking about the gear ratio, which is also often called the speed ratio. And the gear ratio is the number of rotations of the driving gear to the number of rotations of the driven gear. So the driving gear is the one initially doing the rotating, and the driven gear is the one that receives this rotational force. And the gear ratio can be calculated by dividing the number of teeth on the driven gear by the number of teeth on the driving gear. And the speed of each gear is inversely proportional to its size, whether we're talking about the diameter or more commonly, the number of teeth. So this is to say, the bigger the gear, the slower, and the smaller the gear, the faster. So let's take a look at an example where we have 2 different systems of connected or meshed gears. They're not directly meshed in this case, but they use a chain. So in this case, we see that in A, the driven gear has fewer teeth than the driver gear, and B shows the opposite case. The driven gear has more teeth than the driver gear. So again, let's refer to our formula for the gear ratio. So in the numerator, we have the number of teeth on the driven gear. So in A, we have a driven gear with less teeth, and in B, we have a driven gear with more teeth. And then oppositely, in A, we have a driver gear with more teeth, and in B, we have a driver gear with less teeth. So that means that it is B that will have the greater gear ratio, because the driven gear has more teeth, this is the term in the numerator, and the driver gear has fewer teeth, and this is the term in the denominator. So a good way to summarize and remember the important points, or rather the consequences, the implications of the gear ratio, is that a higher gear ratio translates to more speed and less torque, where a lower gear ratio means less speed but more torque. Let's talk about speed and direction, and we'll start by looking at a gear train. So first we have our illustration from the start of this video, and we can notice a few things. Each of the gears that comprise the gear train are of the same size, and they have the same number of teeth. So let's first start by considering the direction. Let's assume that this gear on the left rotates clockwise. So this would correspond to what we see in A. So if this gear is rotating clockwise, we know that for any two mesh gears, the adjacent gear must be rotating in the opposite direction. So therefore, the middle gear will be rotating counterclockwise, and the gear next to that, which is directly meshed, will again be rotating clockwise. If we want to consider what their speeds would be, well again, we noted at the beginning that all of these gears are the same size, and we know that they all have the same tangential velocity. So therefore, they will all also have the same rotational speed. Now, the system on the right is obviously a little more complex, and we won't go through it in full, but we can walk through a little bit of the system to see how speed and direction propagate. So we can start with what's labeled as gear A, which is this green gear attached to a shaft, which is shared by the larger blue gear. So for example, again, let's assume that gear A rotates clockwise. Well, it's on a shaft, and to that shaft, the blue gear, is also connected. So that means all of these will be rotating clockwise. But then we see that the blue gear is meshed with this larger yellow gear. So if the blue gear is rotating clockwise, then we know the yellow gear will be rotating counterclockwise. But what about the speed? Well, again, if they're on the same shaft, then we know the green gear A and the larger blue gear will be rotating at the same speed. But we see that the blue gear that is meshed to the yellow gear will be smaller than the yellow gear. So if they have the same tangential velocity, but the blue gear is smaller, that means the speed of the blue gear will be greater than the speed of the yellow gear. And you could continue this analysis through each meshed gear in the system to understand their relative speeds and directions. So let's also talk about what's called belt drives, which is very similar to gear trains, and we can consider the speed and direction in them as well. So we'll consider two systems just the same as we did before. So we'll start with this wheel A, that is to the far left of the belt drive. So if this is rotating clockwise, as it is indicated by this red arrow, let's see what direction we expect that the wheel B will be rotating. Well, the difference between wheels in a belt drive and gears in a gear train is first of all that we won't have that opposite rotation direction between adjacent elements. So for example, we see that the wheel A is rotating clockwise. Does that mean that this second wheel will be rotating counterclockwise like we might expect in a gear? Well, no, it will actually be rotating in the same direction so long as it is on the same side of the belt. So for example, this wheel A is on the inside of the belt, and this wheel is also on the inside of the belt. They are on the same side, which means they'll be rotating in the same direction, and they are both therefore rotating clockwise. Now if we see, actually all of these wheels are on the inside of the belt. So actually, B will also be rotating clockwise, as will all the other wheels in the belt drive. Now we can consider one more case which has a bit of a twist, no pun intended, as you will see in a moment. So in this case we have wheels which are attached to shafts, and we have belts that connect them. So again, for example, let's say that this wheel is rotating clockwise. Well, if that wheel is rotating clockwise, what do we expect for the above wheel? Well, they're both on the same side. They're on the inside of the belt, so it should be clockwise, right? Well, no, actually, because when you see a twist in the belt like this means you can expect an opposite direction of rotation. So in this case, this wheel would be turning counterclockwise. And just as before, you could use these same principles to continue this analysis through the system. So we covered a lot in this video, so let's summarize some of the most important points. First of all, a gear is a type of simple machine used to manipulate the magnitude or direction of a force. And gears are used in combination and are linked together by their teeth. And when you form a system of linked gears, this is called a gear train. And by using interlocking teeth that mesh with another gear, rotational force can be transmitted between gears. Then we have the gear ratio, which is arguably the most important concept to know and understand in the context of gears. And the gear ratio can be calculated by dividing the number of teeth on the driven gear by the number of teeth on the driving gear. Then we have our 3 important things to know about meshed gears or system of meshed gears. 1, any 2 meshed gears will rotate in opposite directions. 2, when 2 gears are directly linked, their tangential velocities are always the same. 3, larger gears rotate more slowly than smaller gears if they have the same tangential velocity. And then we have our summary of the effects of gear ratio, which is that the higher the gear ratio, the more speed but the less torque. And then conversely, the lower the gear ratio, the less speed and the more torque.